And here we are, back with James.
Hello, Howard.
How are you?
Nice
Okay?
to see you again.
Fantastic. And here we have your model engine.
We have indeed. We've got our KJ66 model gas turbine made in a average model engineering workshop by myself, and very powerful little machine which we'll be demonstrating shortly. Very simply, we've got this centrifugal compressor at the front, axial flow turbine at the back, and a vaporizing combustor in the middle, and we have kerosene as our primary fuel. Doesn't vaporize at ambient temperature, so we actually have to introduce a little bit of heat, which we do with just a little bit of gas, butane, normal butane mix.
Came in your pocket, fantastic. Kept it nice and warm.
Keeps it nice and warm with a cool day like today. It just makes sure that things are moving. So that will actually help warm up the engine before we start introducing the kerosene. And once that's hot, kerosene goes in, the whole thing then can get up to speed, and we'll be running at an idle speed of 36,000 RPM. Oh. And full power is achieved at 120,000 RPM, at which point we have 5 cubic feet of air per second going through the intake, heated to 850 degrees centigrade. So if you can imagine 5 cubic feet of air every second being heated from 20 up to 850 degrees.
That's a lot of pressure.
That's a lot of energy, a lot of pressure.
Yeah, fantastic.
And so the only way it can actually come out of the engine is through the exhaust, and because of that, air is expanded so much at that temperature, it comes out very, very fast, very nearly 500 meters per second.
Amazing. Well, we're looking forward to your presentation, which is actually about to start.
It is. Right, we are the Gas Turbine Builders Association. We're simply a group of enthusiastic amateur model engineers who love things that spin very fast and burn very hot. Gas turbines. What we've got here is an example of a homemade gas turbine. This is called a KJ66, and very simply the 66 is just the size of the rotor. So we've got a 66mm centrifugal compressor at the front, a 66mm axial flow turbine at the back, and a vaporizing combustor in the middle. And our primary fuel is paraffin or kerosene. Now that doesn't vaporize at ambient temperature, so what we actually have to do is heat the vaporizer system up, and all we do is introduce a bit of propane butane at the very beginning during the startup, and that gives us enough heat then to get the fuel running. So in order to start a gas turbine, rather like a car or so any 4-stroke engine, when you turn the key, a little electric motor comes in on a Bendix, turns the engine over, starts the full cycle process, and away you go. With a jet engine, much the same. We've got a little starter motor at the front here. There's a Bendix drive inside, which then locks onto the rotor and starts the rotor turning. So although this rig looks very, very complicated, computers and everything, this is a research and development rig. The only bit that's actually used to run the turbine is a tiny little box just down here, and that runs the whole thing. So when I command it to start, first thing it does is spins over the starter motor. There's a little RPM sensor here which detects that rotation. And the box says, okay, right, we've got a free moving rotor. It'll turn on a gas solenoid valve here, lets the gas in. There's a glow plug here, turns that on. And so what we should have is a little bit of a whir and a pop as the gas ignites. The starter motor will then just turn the rotor over whilst the vaporizers warm up. Thermocouple at the back end here. Once it goes above 100 degrees centigrade, then it says, okay, we've got the heat. Turns the fuel on, and we start introducing the kerosene. You get a pickup of energy. You'll hear when that kerosene starts going in as that energy rise from the kerosene. As the temperature then goes up through 350 degrees, automatically the gas is turned off because we now know that the kerosene is burning. So gas is off, and we're then running on the kerosene. All the time the starter motor is actually accelerating the rotor. And with a jet engine, what we have to do is achieve what's called the self-sustained speed. That's the point at which there is enough energy in the gases coming through the turbine, so enough temperature and velocity passing through the turbine that it can drive the compressor without any external mechanical input, i.e. without the starter motor. On this engine that happens at about 22,000 RPM. So the starter motor will continue up to about 24,000 RPM, so we're well within that self-sustain zone. It will then drop out and there will be enough energy in the turbine to then drive the rotor up to its idle speed, which on this engine is set at 36,000 RPM. So at 36,000 RPM, the little box says, okay, we've got good RPM, we've got good exhaust gas temperature, all looks good. You can have authority on the throttle. Up to that point I can do what I like with it and it will ignore me. So I will then be able to just go through the throttle range, show you what it does. Maximum power is achieved on this particular engine at 120,000 RPM, at which point it is sucking in approximately 5 cubic feet of air per second, heating that air up to 850 degrees centigrade, which makes that air expand dramatically, and the only way out is through the turbine. So it comes out through the turbine very, very fast at just under 500 meters per second. So what we're taking air from standing still and accelerating it to just under 500 meters per second, and that's what gives us our thrust. And so this engine weighs approximately 1.5 pounds or 3/4 kilogram, but it will at maximum power be producing approximately 16 pounds of thrust, or 7 kilograms, near 7 kilograms of thrust. So a very high power to weight ratio. So if you want to put this on a model aircraft, for instance, as long as you can keep your aircraft weight down to around that 7 kilogram mark or just below it, then you have vertical flight capability. So just go straight up. Most of us don't do that. Most of us obviously build slightly bigger and more heavier and have a slightly more sedate flight style. These engines can actually be used on anything. This is a pure turbojet. A pure turbojet basically means that the air coming in through the intake, all of it goes through the combustion chamber. So what comes out the back end is very hot and very fast. So you actually lose a lot of energy into the atmosphere because you can't use it all. Making use of some of it as thrust, but it's amazing how much is left behind. A lot of our other engines, we've got a locomotive in there which is turbo electric. So we have what's called a free power turbine, which is not connected. It's like a big windmill in a hot, fast wind. And that then turns into shaft power through a gearbox, and we can get much more energy inside the engine and make use of it much better. Which is why on a commercial airliner you've got that big fan. And that is actually producing 80% of the thrust from that engine, and the little jet engine in the middle, which is driving it, is actually producing very little out the back end, which is why it's very powerful but remarkably quiet by comparison. Now when it comes to noise, when I start this up, when you see me put this on, I would recommend fingers in ears. Mainly because these are actually remarkably quiet on a model aircraft. If you fly one of these on a model aircraft and somebody else is flying an internal combustion engined aircraft, you can't hear the jet. So we tend not to fly together because it's very disorientating for the jet pilot because he doesn't know if it's running or not. But in this environment, because we've got a nice shiny metal floor, shiny metal walls, and even the canopy above us bounces noise around everywhere, so just fingers in ears is a safer bet. So when you see me put those on, natural reaction probably will be from most of you to do it anyway, but I'll just mention it. Anyway, let's see if we can get us started. So keeping all the batteries in my pocket on a cool day to just keep the energy levels up. Right, let's see if I've got a spare bottle of gas because this one's getting a teeny bit low, but we'll see if we can get it. It doesn't need very much. Okay, let's see if it'll go. Okay, and that's all it does. To start any stop any gas turbine, the only thing to do is actually switch the fuel off. So what happens is you actually run down at full operating temperature, say inlet temperature of 850 degrees centigrade. So you probably noticed I actually switched off the fuel and shut the throttle at about half throttle, which meant it actually, as it spooled down, it actually sucked in a lot of cold air to help it cool down. But even that's not cooled it enough, so what's happened now is the starter motor has now reconnected and is now pulling in more cold air, and it will continue to do that until we reach about 100 degrees, which it has just done. So it's now stopped. And the reason we do that obviously is for the life of the bearings. So you can imagine those sort of temperatures and those sorts of speeds, the bearings have to be reasonably specialised. They are just, in fact, 2 bull races in there, but they're marginally unusual bull races. They are standard steel inner and outer races, but they are ceramic balls, and there's no cages. So they're what's called full complement angular contact hybrid ball races.
Say that again.
Only once at a day. And what we also do is we add a little bit of lubricant into the fuel. So to all intents and purposes, it's a 2-stroke jet engine. So what we do is, as that fuel comes through the pump, we actually have a little T-junction and a restrictor. So a tiny amount of that fuel oil mix gets put in front of the front bearing behind the compressor, and at the kind of speeds we were running, I was actually up to 110,000 RPM during that display. As it hits that fast rotor, those little drops just atomize, you just explode into millions of atoms. We also bleed off a tiny bit of air from the compressor, so we get an oily mist passing through first the front bearing, then the rear bearing, and is burned off on the way out. It's what's called a total loss system. So if you can imagine, the bearing at the back here is approximately that far away from that 850 degree jet stream coming past it. The radiant heat alone is fairly substantial on that bearing. But with this oily fuel air mist passing through them, that rear bearing never exceeds 140 degrees. And these are commercially available bearings. There are 1 or 2 other applications, not just us needing the high speed, the high temperature, so we can actually buy these off the shelf. And the bearings are actually guaranteed for 160,000 RPM at 300 degrees centigrade. So I'm actually working well within the limits of that in this particular engine. We do have engines, the smaller you make an engine, the faster it has to run. And I'm running at 120 to get essentially to get the tip speed at approximately the speed of sound. When you're at a full-size engine, you don't have to turn as fast to get that same velocity at the tip. And we got one engine inside, which is so small that its starting speed, it idles at 95,000 RPM, and full throttle is achieved at 250,000 RPM, and we're still using the same bearings. So the 160 is probably a fairly conservative figure, because we haven't had any problem with that engine either. So,
what's the life of the bearings?
Typically the bearings, one of the difficulties with bearings is because we're taking air, putting through it, it's kind of the cleanliness of the air around you, which sometimes isn't always ideal with the steam and locos around. But typically I usually change them at about 50 hours or so. Usually that's kind of a season's use, and then come the winter time, strip it down, new bearings, ready for the next season, and then you don't have to worry about it during the season. But as long as you have clean air and your good management of your fuel cleanliness, they are very good. And the nice thing about them, because they're dissimilar materials with the steel races and the ceramic balls, actually when you put a brand new set in, they tend to be quite rough. They seem to be rough, and they actually polish the races and they get smoother after just 2 or 3 runs. And then once they're polished, they're just lovely and smooth, and they just go.
Magnificent. magnificent demonstration. Really good.
Thank you. Thank you.